Hi everyone, what's up? Today I want to solve with you a pretty cool example of a definite integral. So today we're going to solve this definite integral. We have the integral from -1 all the way up to 1 of the function x squared dx, okay? So now this is a pretty easy definite integral to solve, but today I want to emphasize something very important about definite integrals and even functions, okay? So in this integral, we have a function that is even. Remember, x squared is going to be a parabola. If you flip it, you're going to get back the exact same function, okay? So x squared is going to be an even function. And let me show you something about the graph of this parabola. So let's say we have something like this. Okay, yeah, this looks better. So as you can tell, I'm not very good at making graphs, but this is decent, this is sufficient for what I'm trying to show you. So basically we can represent this integral as trying to find the area from, I'm going to say this is -1 and this is +1. So we basically want to find the area enclosed in this region over here, okay? So we can write, we can make a line over here to mark the limit, or our bounds of integration. So we basically want to find the area in these two regions, okay? And we basically want to add the area in these two regions. Now, that thing that I just said, add the area between these two regions, well, it's a very interesting idea for this function, for x squared. So x squared is going to be parabola centered at 0, okay? Which means that its axis of symmetry is going to be x equals 0. Now, that is really good because that means that the axis of symmetry of this function, and therefore the axis over which, if you flip it, the axis that if you flip it is gonna flip over, is gonna flip with respect to, yeah, I think that's correct. So this is gonna be an axis, and if you flip it, well, it's gonna flip with respect to the axis x equals 0. That's my point. And that axis, you can see that it's exactly in the middle of the integration interval, okay? The middle of -1 and 1, the middle x coordinate is going to be x equals 0. That is really good because that means that the right hand side region is going to be exactly the same as the left hand side region, okay? And that means that, well, we can actually, to compute this area, we can compute the area of one of these regions and then just multiply by 2, okay? Because we have 2 of them. So, computationally, this would look something like this. So this is going to be, the definite integral can be computed as the definite integral from 0, so this is going to be 0, this is 0, is going to be the definite integral from 0 all the way up to 1 or -1. So you could actually write plus or minus 1. No, actually, no, never mind, you cannot write -1. I want to emphasize that, well, you can go from -1 to 0 or from 0 to -1, but you cannot go from 0 to plus or minus 1, okay, that would not work. You would have to multiply by negative in front. But yeah, anyways, imagine I never said anything about writing plus or minus here. So this definite integral can be computed as the definite integral from 0 to 1, or from -1 to 0. And I'm going to write the 2 in front, so 2 times this definite integral, and this is going to be x squared dx, okay? So this is the idea that, that I want to convey right now. So these two regions, they're the same, okay? And if you want to find the area in the total region, well, you can just find the area in 1/2, okay? And then multiply by 2, and that's it, okay? Now, for the function x squared, that is something pretty easy to solve, and let's actually do it real quick. So we know this is going to be 2 times, so this is going to be 2 times x to the 3rd power divided by 3, and we have this evaluated from 0 to 1, okay? So now this is going to be the same as if we had, this is going to be 2 times 0. So when we evaluate this function at 0, we're going to subtract by nothing. So we don't have to subtract by anything. And this is just going to be 2 times 1/3, okay? Because 1 cubed is going to be 1. So we just have 2/3, okay? So this is the final result. It's pretty easy to compute. And well, for this example, it might not be, it might not be super useful or super, wow, this is amazing to understand that you can do this trick. However, a lot of functions that you will encounter might be kind of complicated, especially some trigonometric functions or some, some wave functions using Euler's number, E. They might be kind of complicated, but they might be even functions, okay? And if they are even functions and their axis of symmetry is in the middle of the integration interval, then you can use this trick, okay? I just wanted to use x squared, because it's a pretty simple function, and I think, it helps me support my points pretty effectively, okay? But, that's what I wanted to show today, okay? So yeah, that's been the entire video. I hope that you enjoyed it. Remember, this trick is pretty helpful if you're dealing with functions that are, curvy or wavy. You might be encountering an even function, and if it's pretty hard to compute, it's antiderivative, or it's just simply too much to write. Well, it might be better, to just grab the interval from 0 to 1, or from any number to another number, and such that those two numbers represent half the interval that you have, and then just compute it from there. So this is something really helpful to have. So yeah, that's been the entire video. I hope that you enjoyed it, and see you in the following one. Bye.